Suppose we have two coins. One of the coins is 3 times the radius of the other coin. This also means that the larger coin has 3 times the circumference of the other, because the circumference is 2 pi times the radius. If we roll the small coin around the outer edge of the large coin, without it sliding or slipping, how many times will the small coin rotate about its centre? The result might not be quite what you expect. In this video, we will learn why that is the case. We will also see how this effect relates to the orbit of the Moon around the Earth. If the circumference of the small coin is c, then the circumference of the large coin will be 3c. Let's start by simplifying the problem. We can imagine rolling the small coin along a flat plane for a distance of 3c. How many times will the coin rotate? Well, if it rolls without slipping, it will travel a distance c in one full rotation, so we would expect the coin to rotate 3 times as it rolls a distance of 3c. If we try it in real life, that is exactly what happens. So surely the same will apply if we roll the small coin around the larger coin. It is still rolling the same distance after all. Now let's test this. In this animation, the small coin has a marker, initially pointing downwards, so we will be able to see how many times it rotates. We will roll the coin until the marker is pointing downwards again. This happens after a quarter of a turn. That might not be what you expect. If we carry on rolling, it happens again after another quarter turn, then again after another quarter turn. By the time the coin is back to its original position, it has rotated 4 times, not 3 times. How can this be if it has only rolled a distance of 3c with no slipping? This isn't some animation trick, as we will see next. You can try this with real coins or any other kind of disc and get the same result. If the small coin was half the size of the big coin, it would rotate 3 times. If it was a quarter of the size of the big coin, it would rotate 5 times. There will always be one extra rotation. Where does it come from? We can gain some insight by looking at the rotation of the small coin relative to the large coin. When we start, the line on the small coin is pointing at the centre of the big coin. If we roll the coin until the line points at the centre once more, then we can see it has gone a third of the way around the big coin. But of course, from our perspective, the small coin has rotated by more than a full turn. After rotating another third of the way round, it is pointing at the centre once again, and after another third it is back where it started. So relative to the large coin, the small coin has only rotated 3 times. So you can see the animation wasn't cheating. But where does the extra turn come from? If we compare the coin rolling along a flat surface to a coin rolling around another coin, the obvious difference is that the second coin is travelling around in a large circle, as well as rolling about its centre. If we place the small coin on a turntable, we can see the effect of going round in a large circle without rolling. After half a turn of the turntable, the coin is upside down. In other words, it has effectively rotated through half a turn about its centre. After another half turn of the turntable, it is back to its original orientation, so it has effectively rotated through a full turn about its centre. Combined with the 3 turns from rolling around the edge of the coin, that makes 4 turns in total. To look at this in a slightly different way, imagine the coin rolling around the outside of a square with sides length c. Remember, c is the circumference of the small circle. As the coin rolls along the first side of the square, it rolls a distance c, so it performs 1 full rotation. The coin then rolls over the first corner, which adds another quarter turn. Then it rolls along the second side and over the second corner. This adds another full rotation plus a quarter rotation. It then rolls along the third side and corner, which adds another 1 1/4 rotations, and the fourth side and corner to return to its original position. That is a total of 4 full rotations plus 4 quarter rotations, which is 5 in total. Just like the circular coin, the number of rotations is equal to the linear distance in multiples of c, plus 1. In the case of the square, these two effects are separated. With the circular coin, they are both happening simultaneously. There is a completely different way to look at this, which some people find clearer. That is to look at the distance travelled by the centre of the coin. The rule is, every time the coin travels a distance c, the coin will go through one full rotation. In the case of the small coin rotating about the big coin, the centre of the small coin goes round in a circle, but that circle is bigger than the radius of the large coin. In fact, the centre path radius is the sum of the radii of the big coin and the small coin. That makes it 4 times the radius of the small coin. This means that the circumference of the centre path is 4c, so the small coin must rotate 4 times, which of course it does. As the moon orbits the Earth, we always see the same side, the near side. We never see the dark side of the moon. From our perspective, the moon doesn't rotate. The reason we see the same side of the moon all the time is that the moon itself rotates on its axis exactly once during the time it takes to orbit the Earth. It takes a little over 27 days for the moon to orbit the Earth, and it takes exactly the same time for the moon to spin once on its axis. The two times aren't just similar, they are almost identical. This is no coincidence, of course. It is due to tidal locking. In this scenario, we are the large coin, and to us the moon doesn't appear to be rotating at all, but to a distant observer, the moon's rotation will be visible. If you enjoyed this video, please subscribe, or join my Substack newsletter at graphicmaths.substack.com.